this video, I want to look at the application of momentum to fixed axis rotation or strict rotation of a body without any additional linear translation. So when we talk about momentum in rotation, first we want to look at, again, our arbitrary rigid body, which has some center of gravity g. And for example purposes, we're going to say there's some point over here which we'll label O, and this point is going to form the basis of our fixed axis rotation such that there is some measurable distance between O and G, which we might label R sub G. So this would be like a position vector R between O and G. Now, because this is fixed axis rotation, where we have some angular velocity, we know that the velocity of G has to be perpendicular to the vector R, so we'll call that V sub G, and we know that there's a relationship there between the two. Because that velocity exists, and we have this rotation happening at the same time, from a momentum standpoint, we know that the linear momentum is again going to have the form of mass times velocity of the center of gravity, and this vector, momentum vector, basically is going to look exactly the same as our velocity vector over here, directed along that line. Now we can look at the angular momentum of this rigid body, because we do have rotation, and the angular momentum about the center of gravity G is going to be equal to I, so the mass moment of inertia about the center of G, so subscript G, times that angular velocity. So, you know, from a translation standpoint here, this looks exactly the same in terms of the form of the linear momentum, in that mass becomes mass moment of inertia, linear velocity becomes angular velocity, and it all looks the same. Now, suppose instead we'd rather, perhaps for convenience, calculate the angular momentum about the rotation axis O. We can do that, and if we do that, we can take into account, again, the rotation about G, so I'm going to pull that same term down. But now, because we're rotating about a different axis, we have to take into account that that center of gravity itself is moving, and I'm going to add on the term here, R subscript G, so that position vector times the linear momentum, in this case, mvg. Now this will look fairly similar to what we saw when we applied the equations of motion to a rotational system, in that we can do a summation of moments, and we can take the mass moment of inertia about different points and reframe the equation in different ways. Another way to think about this angular momentum about the axis O is as the mass moment of inertia about point O. So in this case, we aren't having to add on this additional term, RMVG, because we're taking the mass moment of inertia explicitly around the rotation axis O, rather than in this first equation we were taking the mass moment of inertia around G. However, if we look at this and kind of realize, well, the next thing we're going to have to do is compute the mass moment of inertia around the axis O. So if we express that in terms of something we often know, which might be the mass moment of inertia around the center of gravity, plus a parallel axis theorem term, which would look like this, and then carry the angular velocity over, what we can see is that basically this expression ends up being exactly the same as the one above if we realize or remember that Vg equals Rg omega. So if we substituted this in to either of these expressions here, we would show that these two equations are equivalent. So it's really, again, two different ways to look at the same thing, or to think about it in two different ways. And it looks exactly like what we saw when we applied the equations of motion to a fixed axis rotation system. So hopefully it's all kind of coming together, that these are all different ways of looking at the same thing, slightly different quantities that we're looking at, and we can evaluate them in using much of the same tools. All right, thank you.